So welcome to lecture number 44 of the statistical thermodynamics course. So we wrote what is called the partition function for the combined Ro-vibrational model. So again, using Euler-Maclaurin expansion, okay, with theta RV by T, okay, this will lead to Z RV equal to Z RV. There is a 0, then there is a Z correction term. Okay, so here, of course, Z RV 0 is given as 1 over sigma 1 over y 1 minus E minus T. Okay, and Z correction can be written as 1 plus y by 3 y squared by 15 T gamma by y. So it's a long expression, just bear with me, plus delta by T minus 1 plus 2x star into T ET is 1 square. So if you look at these three equations, okay, out of this represents what we call a first order correction. Okay, to the simplex solution. Okay, and this however tells you it's an auxiliary second order correction. Okay, so in essence, the total partition function then becomes, this is the total partition function. It is ZTR, Z electronics, Z naught RV, and then there is a Z correction. Okay, where your Z electronic is given as J GEL J e to the power of minus EL J by KT. So all terms, except you can see this particular term over here, can be calculated in the same fashion as for the rigid rotor harmonic oscillator model, except that you use T and Y instead of theta V by T and theta R by T. Okay, so using this same principle, therefore, now you can calculate the differentials, the usual derivatives, right? So this is T ln Z RV divided by dt at constant volume. This is given as 1 plus T by dt minus 1 T ln Z correction divided by dt at constant V. Okay, and then of course you have T squared ln Z RV by dt. Close the loop. Constant V is equal to 1 plus T squared ET by ET minus 1 square plus E by dt square Z correction divided by dt. So the first, if you look at these two terms, okay, of both the equations, the first two terms of this equation, plus sign here, okay, that obviously arises from this. They obviously arise from this. Okay, hence all Ro-vibrational contributions to the thermodynamic properties are obtained by simply adding a second order correction term to the primary terms which are closely associated with the rigid rotor and the harmonic oscillator model. Okay, so furthermore, we can write T ln Z correction divided by dt at constant volume is equal to the first derivative divided by this correction. Okay, and in this way you can write all the other expansion terms also, okay, in this particular fashion. And just let me write down the correction term. It's y by 3 minus y squared by 15 to gamma by 15 plus t delta et minus 2x star divided by dt minus 1 square plus 4x star e square et divided by et minus 1 cube. So in essence, this is the example of how to use the semi-rigorous model to find out the required terms for, U, LP, and C. Okay, so this brings to a partial closure that, we have found out ways in which you can calculate. So you have the simplex model, we have the more complex model. So we have done how to do diatomic gases, more or less. Okay, of course, there is a polyatomic gas as well, which is outside the scope. But we can say a few things that when you evaluate the thermodynamic properties for a gaseous assembly composed of polyatomic molecules, it depends on whether the associated molecular structure is linear or nonlinear. For example, linear molecules are carbon dioxide is one example. Okay, so there can be here the atoms are basically arranged along a single Partition, whereas for water it is very different. Okay, so that means the geometric arrangement actually dictates whether how many rotational degrees of freedom there could be. For example, linear polyatomics has got 2 degrees of rotation, whereas nonlinear can exhibit 3 such degrees of rotation. Okay, so for polyatomics, just as a very brief thing, if it is linear and then there is nonlinear. Okay, so translation is basically the same. Rotation, you have 2 versus 3. Then of course vibration. Vibration is 3n minus 5 and 3n minus 6 respectively, if it is composed of where n is the number of atoms. As you can see that each vibrational mode designates an internuclear distance or angle whose oscillation reflects a local electronic potential. So we are not covering this, but this is something that you can read. Once again, you can do a similar type of separation, complete mode separation, and then you can, like in a diatomic molecule, you can evolve a set of rules to how to take care of this. So we are going to stop here and we are going to shift a little bit towards spectroscopy and see how spectroscopic measurements for concentrations, temperatures, etc. can be performed. Okay, so let's try to look at now the problem of interaction of radiation with matter. The interaction of radiation with matter. Okay, so here we bring first the concept of Einstein A and B coefficients. We'll see what this means in a second. Coefficients. So the first consideration is consider the collection of in two-level systems. Okay, say in a volume 1 meter cube. Okay, where the upper energy level is E1 and the lower energy level is E0. The upper energy level is E1 and the lower energy level is E0. So these are the two energy levels. This is E1 and this is E0. Okay, so there is N1 and N0 are the number of particles in each of these energy levels. Okay, so if the number of systems, so if we write it like this, if the number of systems with energy E1, is N1, and number of systems with energy E2 is N2. Okay, so and this system is at a constant temperature T, with constant temperature T, and bathed by radiation density T. Okay, so this is the state of the system, and we can also say that this system, let's assume that this system is in thermal equilibrium. Okay, assume the system is in thermal equilibrium. Okay, is in thermal equilibrium, and the populations N1 and N1 plus N0 is equal to N. Okay, so that is the population. And they are related, N1 by N0, EHV10 by KT, where 10 is nothing but E1 minus E0. Okay, so this is the state of the system. Okay, so the idea is therefore, so gamma 10 is basically the difference in the energy between the two levels, right? So let us redraw it in a little bit. Again, the same thing. So this is E1 N1, this is E0 N0, and let us draw a few lines, and then we will see what those things are. This is B01. One to 0. Just hold on and we will explain what these lines actually means. Okay, so we are writing a few things, and E minus E0 equal to H. Okay, so this is the expression that we have. So there are three possible ways. So because see, the system is in thermal equilibrium. So there are three possible processes that can change the state of the system from E0 to E1 or from E1 to E0. Okay, so there are three possible processes. Three possible processes can change the state of the system, from E0 to E1 or E1 to E0. Okay, so these processes are, if we write it, there can be absorption. Okay, there can be something called spontaneous emission. Okay, and then there can be something called stimulated emission. Okay, so when this particular system is now bathed with radiation, okay, so what happens when absorption results from the presence of a radiation density of a precise frequency that is needed to drive a transition from the ground state to the excited state. So let us draw the different types of transitions so that you are able to get it properly, that what is absorption, what is spontaneous emission, and what is stimulated emission. Absorption Let's do this one first. Okay, so this is what the system looks like. Blue. Okay. So this is a system. This is before, and this is after. So after, what happens? After the absorption is over, this particular particle is now at an excited stage. Right? So this process is called absorption. Then, of course, there is something called spontaneous emission. So let's take this. Let's take this. Okay. So in case of this spontaneous emission, what will happen? There was something at the excited stage. So now this is coming back to the ground state. Okay, and there is an emitted radiation. Okay, so that is good. Now we come to the something called stimulated emission. Okay. This is what stimulated emission looks like. Okay, so there was this at the excited stage. Now you have H mu. Okay, that is hitting this. All right. So now what happens is that in the next, you have now the particle now residing in the ground state, but there is 2 h nu amount of energy that is released. Okay, so this is called stimulated emission. So this is spontaneous emission, and this is absorption. So it is clear that how the energy diagram should work, right? Okay. So this is for a two-level system, right? So absorption results from the presence of radiation density, which is rho v, okay, of a precise frequency which is needed to drive the transition from the ground state to the excited stage. So let's write it. dN1 by dt. That is, there is a change in population at the upper energy level, and this is driven by V0 to 1. There is a radiation of precise frequency into N0. Okay, so this is basically nothing but a rate constant, also known as Einstein absorption coefficient. Einstein absorption coefficient, or B coefficient. All right, so this is called a rate constant. This rate constant is actually what is called the Einstein B coefficient or absorption coefficient. So the system, so you can understand, so there is a change in the population at the upper energy level, okay, when it is being hit by a radiation of a particular frequency, of a precise frequency, which drives a transition. Some particles or some systems are promoted to the N1, to the E1 level, basically. And this is the rate constant that you see, which is precisely what we have drawn here. Okay, this is the rate constant. So this is the B coefficient. All right, so okay, so that's good. Now, similarly, if the system is already in an excited stage, okay, so if the system is already in an excited stage, state, comma, already in an excited state. Okay, then a photon energy H10, okay, can induce the system to make a transition to the ground state. To ground state. Okay, so that means dN1 by dt will be given as minus this time. So this is 1 to 0 rho v v10 into N1. Remember, this is N1, not N0. Okay, so this is called the stimulated emission coefficient. Okay, so finally, if a system is already in the excited, so this is a system which was there in the excited state, you are just hitting it with a photonic, with a particle of light, and it induces a cascade or a transition to the ground state, and 2 photons are emitted in the process. Now, finally, if the system is also in an excited stage, it can spontaneously emit a photon also. If the system, without any interaction, in fact, with radiation, in excited state, okay, can spontaneously, emit a photon at a rate dN1 by dt equal to minus a 1 to 0 into N1, where this is basically the A coefficient. That's why the name Einstein AD coefficient. Okay. So since the system is at equilibrium, the rate of population of the excited state by absorption must balance the rate of depopulation by stimulated and spontaneous emission, right? So if the system is in thermal equilibrium, okay, the rate of population of excited state by absorption must balance, okay, the rate of depopulation by stimulated and spontaneous emission. Isn't that correct? Okay, spontaneous emission. So in other words, N naught B10 E is equal to A to 0 N1 plus B1 to 0 rho V to N1. Right? So this is the equation that we can write. And then on the top of that, we have a ratio of N1 by N2, N1 by N0, right? We already have a ratio of N1 by N0. So N1 by N0 is given as E minus H by KT, which is equal to, therefore, is equal to B 0 rho V divided by A into 0 plus B 0 rho V. Okay, this is what it is, right? So if you now solve for rho V, the equation, if you solve for this, then rho V 0 is equal to A 1 to 0 divided by E H1 naught by KT minus B 1 to 0. Okay, this is what you are going to get. Okay. Where your rho also V10 is given by the Planck's function. So it is 8 pi h cube divided by c cube 1 by e to the power of h1 naught by kt minus 1. Okay. So if these two expressions have to be valid, so we come to the next class, that what are the necessary conditions for these two equations to be valid in the first place. Okay, so these are both equivalent expressions, right? One is given by the Planck's function and one we just now derived, okay, by this simple two-level systems. So therefore, now we will see what is the end product of this kind of an arrangement. So that we will see in the next class, and we will continue this particular lecture and see how this can be used for, concentration measurements and stuff like that.